Students, welcome to my YouTube channel. In this video lecture, I am going to answer questions from sample paper number 3, the fourth edition of the navigation book, RK Bali navigation book. So let's begin with question number 71. An artificial horizon has dash degrees of freedom in the dash axis. So artificial horizon has 2 degrees freedom in what axis? In the vertical axis. Factual question. So remember all the degrees of freedom of all three gyro instruments, the respective axis of rotation also. Next, when both the needle and ball of a turn and slip indicator are displaced to the right, aircraft is turning right with too much task, aircraft turns right with insufficient task, turning left with too much task. So here, both needle and ball are displaced to the right hand side. So let's say this is your turn and slip indicator. This is the inclinometer. Okay, and they are displaced to the right hand side. That means this miniature aircraft will be displaced to the right hand side, and the ball is also displaced to the right hand side somewhere here, let's say. Now this is a condition. You're turning right, aircraft is turning right, aircraft turns right. Aircraft turning right, if the ball also goes to the right hand side, that means this indicates a slipping turn. Slipping turn. Now, why does a slip happen? Slip happens because first reason, too much bank. You want to turn to the right hand side, but you bank the aircraft excessively without using adequate rudder pressure. So too much bank, adequate rudder pressure. The third point is slow true airspeed or insufficient true airspeed or forward speed of your aircraft. If you are turning your aircraft with a very too low speed, what will happen? This too low speed will not enable your aircraft to turn in a coordinated flight, meaning your aircraft has to also go forward, also turn. Okay, so it has to do two jobs at one time. Okay, that is to go forward and go forward in a turning condition or in a turning direction, right? So if you do this kind of turn with very too low true airspeed or insufficient true airspeed, so your aircraft will not be able to make a proper turn to the right hand side, and it will tend to fall towards the center of the circle. So in this case, let's say this is the center of your circle and this is the circumference. Now you're trying to turn your aircraft to the right hand side like this, to the right hand side like this. Okay, so your turn must be coordinated, meaning the ball must be in the center of the inclinometer. It will not remain in the center and fall inside of the turn. That means towards the center of the turn under the influence of centripetal force. If you use too much bank angle, this too much bank angle will increase the centripetal force or the center directed force, inward directed force, right? And if the forward speed of your aircraft is too slow, okay, in order to turn your aircraft you need higher speed, a higher angle of attack, because the lift component gets divided into two parts. One part of lift is used to keep your aircraft suspended in the atmosphere. The other part of the lift component is used as a centripetal force to turn your aircraft around, right? So you must turn your aircraft at sufficient speed. Okay, so if that is not the case, you will be slipping. So the correct answer here is turning right with insufficient task. Turning right with insufficient task. Your aircraft speed is too slow. You will fall towards the center of the circle. You will fall inside of the turn. Okay, so in order to prevent your falling, your speed must be sufficient enough to keep you suspended in the atmosphere. Next, when the turn and slip indicator Needle is displaced right hand side like previously, and the ball is displaced left. What is aircraft doing? So same diagram. I'm going to draw the same diagram. This is your turn and slip indicator, let's say. This is your inclinometer. Okay, so this is straight and level. This is turning. So your needle, right now your needle is displaced right hand side. Needle means the miniature aircraft. It is displaced to the right hand side like this. The ball is displaced left hand side. The ball is displaced left hand side. So this condition. So your aircraft is trying to turn right hand side. Okay, as indicated by this needle or miniature aircraft. But the ball in the inclinometer has displaced to the left hand side. So this indicates what condition? This indicates a skidding turn. This indicates a skidding turn. Your aircraft is skidding. Meaning, let's say this is the center of your circle. You're trying to turn your aircraft around. So this aircraft, instead of turning right hand side, will get thrown away out of the turn, will get thrown away out of the turn like this. Instead of turning inside or turning around, it will get thrown away out of the circle. So this is called skidding. Okay, now skidding happens because of three main reasons. First, your angle of bank is too small. Okay, if you want to turn right hand side, you must establish your aircraft in the right banking attitude. If you don't do that, your aircraft will not have necessary impetus to get to turn. Okay, so low bank angle. Second, the second main reason is inadequate rudder pressure. Adequate rudder pressure. In order to turn your aircraft in a coordinated flight, you must use both ailerons and rudders. So inadequate rudder pressure. And the third is skid happens because you are flying your aircraft at too high a true airspeed, very fast true airspeed. Okay, since the forward speed of your aircraft is very fast, that most of that forward speed or most of the true airspeed of your aircraft is used or consumed in taking your aircraft forward in the forward direction, not around the circle. And that's why you're not able or unable to make a proper turn to the right hand side because the forward speed of your aircraft is too high or very fast, and that fast speed of your aircraft is preventing your aircraft to turn right hand side. So most of the speed is used or the force is used to go ahead, okay, to go forward. That's why if you're flying at very high airspeed, make sure you use sufficient bank angle. If you don't do that, you are going to get thrown away from the center of the circle, right? So the solution is, if you want to fly at true airspeed and you cannot adjust with that factor, you increase the bank angle of your aircraft as necessary, or slow down the speed of your aircraft and at the same time increase your bank angle a little bit and try to establish a balance. So these are the three causes. The solutions are exact opposite of them. So now this is a skid condition. Now skidding happens when the ball is thrown outside of this or out of the center of this inclinometer, and that happens because of what force? Centrifugal force. Centrifugal force is the outside or outward directed force. Centripetal is the inward directed towards the center. Centrifugal is outward directed. So needle is displaced right, that means aircraft is also turning right. So here there is only one option, option alpha, with insufficient bank. With insufficient bank. Which of the following will give the most accurate calculation of aircraft ground speed? DME, ADF, VOR. So correct answer is DME. So DME, a distance measuring equipment. So distance measuring equipment gives the range of your aircraft with respect to the DME ground station, right? So this distance information coupled with speed of radio waves. We know the speed of radio waves. So with these two pieces of information, we can calculate time. If we want to calculate speed, we can calculate the time. Distance is shown by the DME equipment. The equipment can calculate the time it takes for the radio pulses to go towards the ground station and come back. So using speed, distance, time formula, these two pieces of information, distance and time, you can calculate ground speed of your aircraft. So that's why DME station tells us about the ground speed. ADF sighted on the flight route, wrong. ADF equipment tells us the bearing towards the station, relative bearing. A VOR station sighted on the flight route. VOR station tells us the radial we are situated on. It tells us our position with respect to the VOR station, whether we are to the east of it, north of it, northwest of it, whatever. Right? So DME is the only option here. Also remember, let's say if this is your DME station here. Okay, this is your DME station. Your aircraft, this DME station should be lying along your flight route. That means you should be flying either towards this DME station or directly away from this DME station to get an accurate ground speed. If your aircraft is flying parallel to this DME station like this, okay, like this, you won't be getting a DME, you won't be getting a ground speed indication, because when you are flying parallel to the DME station, you are at constant distance from that DME station. Okay, you're neither going towards the station nor going away from the station. So that's why you cannot get distance information or speed information. But when you are flying directly towards this DME station, when you are flying directly towards this DME station, the slant distance between your aircraft and the DME station will keep changing as you move towards this DME station. Okay, the slant distance will keep changing between you and the DME station. This change in distance, the rate of change in distance, how fast this range is changing, how fast you're closing on the DME station or how fast you're moving towards the DME station, this rate can be used to calculate the ground speed of your aircraft. But if you're flying parallel to the DME station, there is no way you can calculate that, because you are at a constant distance from that DME station. So that's why it's very important that your aircraft either flies towards the station or it flies directly away from the DME station. Now, out of these two options, also there can be another option. Your aircraft must be flying towards the station or away from the station. That is condition number one. Condition number two is that your aircraft must be as far away as possible from this DME station. Okay, as far away as possible from this DME station in order for your ground speed to be close to accuracy. Okay, close to accurate. So remember these two conditions. Next, watch my other DME lectures in which I have solved questions of DME from Oxford, RK Bali, Keith Williams. You will understand this concept much more in those video lectures. There are many questions of DME, and the more questions you solve, more familiar you become with the concept and the solutions, and more confidence gets instilled in you. So do watch those video lectures. That will benefit you a lot. When mode C is selected on aircraft SSR transponder, the additional information transmitted is now mode C capability. This mode C capability in your transponder enables to transmit your pressure altitude information to ATC controller, directly to ATC controller. So altitude based on regional QNH, aircraft height based on altimeter setting, flight level based on 1013.25. So option Charlie is the correct answer. Mode C transmits your vertical distance information directly to the ATC controller. This vertical distance is with respect to standard pressure setting 1013.25 hectopascal. Now your altimeter, you may be flying, you may have set local QNH pressure setting in your altimeter pressure setting window. Now irrespective of that setting, the mode C capability of your transponder will continuously and only transmit vertical distance information with respect to standard pressure setting 1013. Remember that. DME channels utilize frequencies of approximately what? Now DME works in the frequency band 962 1213 megahertz. So out of the three options listed here, The only correct the only correct possible answer is option A, which is in terms of megahertz. The other two options, gigahertz, kilohertz, are irrelevant. Question 77. Aircraft DME receiver is able to accept replies to its own transmissions and reject replies to other aircraft interrogations because transmission frequencies are 63 MHz different from each aircraft. Pulse pairs are discrete to a particular aircraft. Pulse pairs are amplitude modulated. Now remember, your distance measuring equipment is based on secondary radar. So let's say this is your ground station. Here is one aircraft, atmosphere, okay, and there is another aircraft, second aircraft here. Let's label them aircraft number 1, aircraft number 2. Now aircraft number 1 will transmit interrogation signals, okay, towards this ground station, okay. This ground station will at a frequency of, let's say, interrogation signal at a frequency of 1090 megahertz. The ground station will wait for 50 microseconds, okay. So ground station, which is nothing but your transponder, will wait for a delay, will wait for 50 microseconds. So there is a delay of 50 microseconds. After that delay of 50 microseconds, the ground station will reply to this interrogation pulse sent by this interrogator number 1 at a different frequency, at a different frequency, which is 63 megahertz removed from the interrogation frequency. That means the difference between interrogation frequency and the reception or the reply frequency will be different by at least 63 megahertz. So let's say the reply frequency is 1030 megahertz, around 60-63. Okay, so this helps aircraft to accept only those reply pulses coming from the DME ground station or the transponder. Any reply pulse, which is just a reflection, which is just a meager reflection from the ground surface, surrounding terrain, obstacles, those reply pulses won't be accepted by the aircraft receiver equipment because those reply pulses will be at the same frequency at which the interrogation signal was transmitted. Okay, so that is how your aircraft is able to distinguish between reply pulses coming from the ground station transponder and reply pulses which are just reflections. So option A is wrong. Okay, so this 63 megahertz difference in reply and interrogation frequencies helps aircraft to identify the signals coming from the ground station, eliminate or disregard signals coming from which are mere reflections from the ground surface. The question is about how your aircraft is able to distinguish between reply pulses intended for itself and reply pulses meant for some other aircraft. So we will look at the second possibility. Now here there is aircraft 1. It will transmit this radar pulses towards the radio pulses towards this transponder. Now this aircraft number 2 will also transmit this radio pulses towards the same transponder. Correct? Now, the radio pulses transmitted by every aircraft will be uniquely spaced, meaning the time interval between this radar pulses will be different for every aircraft. So they are unique to every aircraft. So let's say the time interval between these two radar pulses for aircraft number 1 is 1 microsecond. For aircraft number 2, it can be, let's say, it will be different, 3 microseconds. So that is how this aircraft knows which reply pulse belongs to itself and which reply pulses doesn't belong to itself. Okay, so the correct answer is pulse pairs are discrete to a particular aircraft. Discrete means unique, special to every aircraft. Okay, so option B is right answer. The principle used in VOR bearing measurement is what? Very important, phase comparison. VOR bearing measurement is phase comparison, meaning what? Let's say this is your VOR station. a conventional VOR ground station. This is your north datum. Now this VOR station will transmit one frequency modulated reference signal, a frequency modulated reference signal which is fixed in direction, and the other signal will be amplitude modulated and it will rotate around the VOR station. It will make a 360-degree turn around the VOR station. This is the modulated variable amplitude modulated variable signal. Now this amplitude modulated variable signal will keep rotating around the VOR station. Now in this direction, now currently the diagram that I have drawn, this amplitude modulated variable signal is in the easterly direction. How to know that? The angle between this reference signal and variable signal is 90 degree. That means this will be regarded as radial 090. When this variable signal continues its rotation and let's say it comes down somewhere here. So now the angle between the reference signal and this amplitude modulated signal is 180 degree. Is 180 degree. That means so this particular direction becomes radial 180. Radial 180. So if there is any aircraft which is here, so it will be so that information will be interpreted as aircraft being on radial or positioned on radial 090. Aircraft here that receives whenever an aircraft in this direction receives this variable signal, it will be shown that this aircraft is situated on radial 180. So this is called phase comparison. The phases are compared. The phases of frequency modulated reference signal is compared with the phase of amplitude modulated variable signal. Okay, so this is the principle of operation of VOR. Next, aircraft is flying on a true track 090 towards a VOR station. Okay, towards a VOR station is important on a track of 090. So inbound track 090 near the equator where the variation is 15 degree east. Now the location where aircraft is situated, over there the variation is 8 degree east. 8 degree east. What radial is aircraft situated on? Simple question. So I have solved such questions many times in my other VOR lectures of Keith Williams, RK Bali, Oxford. Now let's say this is your north datum, this is your VOR station. Aircraft is flying inbound track 090. So this is radial 090, this is radial 270. Now it's mentioned in the question aircraft is flying inbound that on a track of 090. So that is only possible when aircraft is flying on radial 270. Okay, flying radial or aircraft is positioned radial 270 flying inbound. So when aircraft is on radial 270 but flying inbound, its track will be regarded as track 090. When aircraft is positioned radial 270 and it's flying outbound, in that case, the track will be an outbound track of 270. So currently our track is 090, so we are flying inbound. Now the variation at VOR station is 15 degree east. Variation is 15 degree east. Variation at aircraft location is 8 degree east. So we know that aircraft is situated on radial 270. But as of now, at this particular step, this radial 270 is with respect to true north datum. All radials of VOR should be or must be in terms of magnetic. So let's convert this true radial, that is radial 270 in terms of true direction into a magnetic direction. To convert true direction into magnetic direction, we take the help of variation, magnetic variation. Now we have two variation values, variation at VOR, variation at aircraft. So remember, whenever solving VOR based questions, use the variation existing at VOR location. For NDB questions, NDB ADF questions, you are going to use the variation available at aircraft location. Okay, so step number 2 will be radial 270 is your true direction. Variation, use VOR variation 15 degree east. So radial in terms of magnetic direction will be what? Now variation east magnetic is least, meaning magnetic direction is less than true direction. So 270 minus 15 will be 255 degree. Correct? 255 degree. That means aircraft is actually located on radial 255. Okay. So correct answer here is radial 255. POR station 61 degree north, 25 degree east, variation 13 degree east. Aircraft 59 degree north, 25 degree east. That means VOR and aircraft have the same longitude. Both are located on the same eastern longitude. Aircraft is located to the south of the VOR station. So this is your VOR station. This is the radial. This is correction. This is the longitude. Aircraft is situated to the south of this VOR station because because the latitude of VOR is 61 north. Latitude of aircraft is 59 north. So you are in the northern hemisphere. So aircraft will be uh, below the VOR. Variation at VOR is 13 degree east. Variation at aircraft is 20 east. Step 1, just looking at a diagram, we come to know that aircraft is to the direct south of the VOR station. So let's say aircraft will be on radial 180. But this radial 180 in terms of true north, we need all our radials in terms of magnetic. So let's convert this true radial into corresponding magnetic radial. How will you do that? You will take the help of variation. Now the variation existing at VOR station. So 180 true direction, variation 13 east, variation is magnetic will be least. So 180 minus 13 is 157. 180 minus 13 will be 167. Correction, 167 magnetic. So that means finally aircraft is situated on radial 167 magnetic. That is the correct answer. And in this case it was 270 minus 15, 255. This is correct. So 180 minus 13 east is 167. So aircraft is located on radial 167. So this is how you do these questions. So this question brings the curtain down on our lecture now. I hope you have understood all the 10 questions that I have done in this video lecture. We had many numericals in this video lecture. So practice these questions multiple times without looking. Set a timer also. Do all the questions in a time bound manner. Okay. If you have any doubts or questions, let me know in the comment box of this video lecture. I request you all to share this video lecture with your friends who are also preparing for exams. Subscribe if you haven't yet and hit the like button if you have liked this video lecture. Best of luck. See you in the next video.